the problem from the Harvard University, -5 whole to the power x equals to 5. And we are to solve for the real numbers x, which satisfies this equation. Now, at first glance, this really looks very difficult because, as you can understand, -5 to the power something that would either produce a positive quantity or a negative quantity, depending on the exponent, if you're talking about integers. Well, so like let's take a few examples. -5 to the power 1 should be 5, and if you do an even number, it should give you a positive number. But -5 to the power something which should produce a positive number, which is 5 itself. That is something which we haven't have an idea of directly, like you cannot guess the value of x directly from here, but we will follow standard mathematical procedures here. So -5 to the power x equals to 5. If we take logarithm on both sides, it looks something like this. So when I say logarithm, I mean natural logarithm. So I will not write base e here, but from now on, we can assume that it is always in base e. Okay. So this is log of -5 whole to the power x, and this is log of 5. Okay. So due to the properties of log, obviously we have x into log of -5 equals to log of 5. So the whole problem basically revolves around finding this part. Now, as you all know, log is not defined for numbers which are negative. So you might have seen before in your calculus 1 courses or in your basic algebra courses that log x is defined when x is greater than 0. Yes, that is true, but that is only for real numbers. Log is also defined for complex numbers, and then the input can be basically anything. We do not really care. So -5, there is some complex number, and to be fair, a set of infinitely many complex numbers, the logarithm of whose basically gives you -5. So first of all, we will write -5 as 5 times -1. And then, if you remember the most important equation in mathematics, or rather the most beautiful equation in mathematics, it was e to the power I pi equals to -1, right? It really connects all four important constants together. This is also true for any. So let's first understand how this comes into being. So like e to the power I pi, right? This is according to Euler's formula. This is cos pi plus I into sine pi. And that is what basically brings about the -1, because cos pi is -1 and sine pi is 0. Now, what happens if you, like, let's say, replace it with other variables, right? So let's say if we were to do something like this, cos of 2n plus 1 pi, we are ensuring that 2n plus 1 is always odd. That means cos of 2n plus 1 pi will always be -1 plus I into sine of 2n plus 1 pi. And any integral multiple of pi with sine always gives you 0. So even this equals -1, right? So that is why what we can do is we want to generalize it for n, because that is important in a logarithm with a negative number inside it, because we can do the principal branch, but then also we can make several other values which will also correspond to log of -5. So there is not a single value which corresponds to log of -5 in complex numbers. Okay. So -5 is 5 into -1, and -1, as we have just seen, is e to the power 2n plus 1 whole into pi into I multiplied by 5. So that should be, because this term, according to Euler's formula, transforms back to this term, right? Okay. Now, log of -5 then should be equal to log of the right hand side. So using formula of logarithm, we can divide this, we can separate this multiplication task into two different terms, which are basically added. So log 5 plus log of e to the power 2n plus 1 whole into pi into I. And this gives you log 5 plus, since the base is e, this thing comes out 2n plus 1 pi I. And now if you go back to our problem, it was x into log of -5 equals to log of 5. Correct? So this gives us the value x is equal to, also we will make some changes right now after we write this expression, log 5 divided by, So log of minus 5, as we know, is now log 5 plus this. So we can do log 5 plus I pi 2n plus 1 for all n belongs to integers. This will work. And you can explain it further by using the fact that 5 is basically equal to 5 into e to the power 2mi pi for any integer m. So you can also write the same thing, and the numerator becomes log 5 plus 2mi pi, and then the denominator becomes log 5 plus I pi 2n plus 1 for all n belongs to integers. And this is the solution to the equation. So if you like this video, please subscribe the channel and like this video, and let me know in the comment section if you want further stuff like this. Thank you.
Hello everyone, welcome to ANS Academy. Today we are going to solve this integral. So this is a fractional part integral, and I chose this integral because I wanted to explain the properties of fractional parts, and I also wanted to explain some properties of definite integration. So by the end of this video, you will be feeling comfortable in both fractional parts and definite integration, because we are going to use a lot of properties here. So look at this integral carefully first. 0 to 1 fractional part of 1 upon kth root of x. So the whole thing is inside the fractional parts, and we have k greater than or equal to 2. Now, it might seem impossible for you to even start this problem if you are not aware of the fractional parts. So I will say that fractional part of x simply means it's a number between 0 to 1 where it cannot be 1. And some examples would be 0.2, the fractional part of this is 0.2 itself. 1.5, the fractional part is 0.5, like that. So it basically gives you the fractional part, not the integer part. Okay. Now, how do we do this? So we will begin with the obvious substitution, x equals to t to the power k. So x equals to t to the power k. With this substitution in hand, we can write dx equals to k into t to the power k minus 1 dt. Notice that the limits remain 0 to 1. So our integral basically becomes 0 to 1. Fractional part of 1 upon, now since kth root of x is then t, this simply becomes 1 by t, and dx as here becomes k into t to the power k minus 1 into dt. This much is done, right? Now we make the substitution u equals to 1 by t. So this would mean that t is equals to 1 by u, and then if you differentiate both sides, it will give you dt equals to minus du by u square. Notice the limits. For t equals to 0, u is infinity, and for t equals to 1, u is 1. Inside we have fractional part of u, k is as it is, let's put it outside, and then t to the power k minus 1 becomes 1 by u to the power k minus 1, and dt becomes minus du by u square. We can simplify this and write this as k 1 to infinity, since the minus sign basically reverses the order of integration here. Fractional part of u divided by u to the power k plus 1 du, and we reach this point, and that is the goal in every fractional part integral of this type. We have to reach something where we have the fractional part in the numerator or the denominator simply as u. Now let's do it from here. So we have this integral now. Now in this integral, notice that fractional part of u, the important property to notice is fractional part of u can be written as u minus the integral part of u. This is the property of fractional parts. Now the integral part of u is basically given by the greatest integer function, and you know that for greatest integer functions, if you put in 1.2, it will give you simply 1. It will always give you the integer, the greatest integer less than or equal to the given number. So that is why fractional part can be defined like this. Okay. Now what we are going to do is we are going to abuse a property of integrals, that it can be broken down into intervals. We are going to break this down into intervals like 1 to 2, plus 2 to 3, plus 3 to 4, and so on. Infinitely many integrals, as you can see. And inside always we will have the function u by u to the power k plus 1 du. Now how to write this formally? What you can do is, since all these integrals would be additions because we are breaking it down, we can simply write k into summation n equals to 1 to infinity, and then integrate from n to n plus 1. What we are integrating? U by u to the power k plus 1 du. Correct? Now we can write now this as n equals to 1 to infinity. Since this u is basically equal to this, we can write n to n plus 1. This as u minus the integer part of u inside the interval n to n plus 1, where n and n plus 1 are integers, is simply n, because n is the greatest integer that is less than u at this interval, right? Because u right now is between n to n plus 1, so integer part of u would be n, right? It is n point something or n. So u minus n, where this part is n, divided by u to the power k plus 1 du. Okay. Now we can integrate this like this. So k summation n equals to 1 to infinity, integration of n to n plus 1, and break it down as like this: 1 by u to the power k minus n by u to the power k plus 1 du. And we reach this point. And now after this we can evaluate it again. Okay, so now we have this integral, and if we can find out this integral and then finally evaluate the summation, we will get our answer. Okay. What we can do is we can write this as k summation n equals to 1 to infinity, and now we have to basically find the antiderivatives. You can use the standard power rule and everything inside the summation. So the first one basically turns like this: u to the power minus k plus 1 by minus k plus 1, and this would be evaluated from n plus 1 to n minus n times. Similarly, u to the power minus k minus 1 plus 1 minus k minus 1 plus 1, and evaluated from n plus 1 to n. Correct? Now write this as k summation n equals to 1 to infinity. Now the first one, what we can do is this: we can put n plus 1 here. So we can write like this: n plus 1 to the power, well, this would be k minus 1, and there is a 1 by 1 minus k common to both of them, so we'll just simply do this here: n to the power k minus 1, and this is multiplied by 1 by 1 minus k minus n. As you can see, this is basically minus k, so is this u to the power minus k. So again minus n, and this minus k, this goes to plus n by k, which is common, and then again we do the same thing: n plus 1 whole to the power k minus 1 by n to the power k. Now this is the summation that we have to evaluate here. Okay. So k summation n equals to 1 to infinity. First of all, this 1 by 1 minus k can be written as minus of 1 by k minus 1. So we should arrange the terms together and then look for how to do it. So this term would basically be 1 by n plus 1 to the power k minus 1 k by 1 minus k minus k by 1 minus k summation n equals to 1 to infinity 1 by n to the power k minus 1.
Bas. Start.
So plus summation n equals to 1 to infinity. Now this term 1 by n plus 1 whole to the power k, and then you have n by k into k, which simply gives you, there is also n here actually, and k cut off basically, and then again you have this sum where you have plus minus summation n equals to 1 to infinity n by n to the power k, which is 1 by n to the power k minus 1, and this is our final summation which we have to evaluate. Okay, so this is the final form which we have for the problem. Before starting this, remember that zeta of p is a number. This is called a zeta function, which is the Riemann zeta function. There are other zeta functions as well. This is defined like this: 1 by 1 to the power p plus 1 by 2 to the power p plus 1 by 3 to the power p, and all the way up to infinity. And in short, in summation notation, you can write this as n equals to 1 to infinity 1 by n to the power p. So this is a standard function, and all even values and almost all odd values of zeta functions are all known. So all even values can be expressed in terms of pi actually, but odd values are irrational and they do not really have a closed form. But okay, we are going to use zeta to give our answer because this is accepted as a closed form answer. Now look at this sum here. So I then would be equal to k by 1 minus k. And this sum here, you see that n equals to 1, that means this sum starts from 1 upon 2 to the power k minus 1 and it goes up to infinity. So basically starts from this point and goes to this point. So if you take from this part, this basically equals zeta p minus 1, right? So what would this equal? This would equal zeta of k minus 1 minus 1, because the power is k minus 1, which is p here, right? Okay, similarly minus k by 1 minus k, this one is directly zeta of k minus 1. So this one is directly zeta of k minus 1. let's come down here. This we can write down as plus summation n equals to 1 to infinity. Write n as n plus 1 minus 1. So introduce a plus 1 and a minus 1 here. So that n plus 1 and this cut off, and it gives you 1 by n plus 1 whole to the power k minus 1, and minus 1 gives you this, n equals to 1 to infinity 1 by n plus 1 whole to the power k. And the last one is simply zeta of k minus 1. Okay, let's do this. This k by 1 minus k into zeta k minus 1, and this one cut off, and we have simply minus k by 1 minus k, right? And from this part we have plus zeta of k minus 1, and this part again n equals to 1, and this is n plus 1. Okay, so this is zeta of k plus k minus 1 minus 1, because this also starts from 2, and minus this one is also zeta of k, right? And this is also starts from 2, and at the end we have minus of zeta of k minus 1. Okay, absorb the minus here and you get k by k minus 1. You see that this zeta of k minus 1 and zeta of k minus 1 cancel, the minus 1 and the plus 1 cancel, and you have minus zeta k. So the answer stands this, k by k minus 1 minus zeta of k. For k equals to 2, the value of zeta 2 is pi square by 6. So if this was a function of k, you can say then I2 simply equals 2 by 2 minus 1, which is 1, minus pi square by 6, which is the value of zeta 2. So this was a very tough problem, but it introduced you to all the aspects of summation and how to interchange between summation and integration, and use these functions like zeta p and the p series basically. So if you like this video, and let me know in the comment section if you want more content of this type, and also if you have any doubts, please let me know that. Also subscribe to the channel and follow for more. Thank you. Hello everyone, welcome to NS Academy. So today in this video we are going to solve this problem. This is a problem from real analysis first year undergraduates, but we can also say this is a problem of the type ISI and CMI subjective. Okay, so the problem states that let fx be a real valued function, and if for x greater than or equal to 1, the function is defined and f1 is given as 1. And we are given that the derivative is simply f dash x equals to 1 upon x squared plus fx whole square, and we have to show that limit x tends to infinity f of x, that it exists and the value is 1 plus pi by 4. Okay, so now let's understand this clearly. Fx is a real value function and it is defined for x greater than or equal to 1, right? Now let's consider this derivative first. So f dash x is simply equal to 1 upon x squared plus fx whole square. Now since x greater than or equal to 1, and this quantity, then this quantity x square is always greater than or equal to 1, and fx whole square, this is always positive. So this whole thing is always positive, right? So we can safely say that f dash x is greater than 0. When the derivative of a function is greater than 0 for all values of x greater than or equal to 1, which is the domain of this function basically, then we can say this is a strictly monotone function. This is a strictly increasing function, right? And what does that mean? That means that for x greater than or equal to 1, we will have fx greater than f of 1. So for x greater than 1, actually we can do this only, because for x equals to 1 the equality holds, and then we have strict equality, right? This thing cannot be 0, so we have a strictly increasing function and not a normal increasing function. Okay, so remember this one, because f of 1 is 1. It is given that f of 1 is 1. Okay. So we will apply the fundamental theorem of integral calculus here. First, remember what it means. A to b f dash x dx, this can be written always as f of b minus f of a. Now since f is a function which is strictly increasing function, so f dash x equals to this, which is greater than 0, we can safely say that limit x tends to infinity f of x can be evaluated. Now it remains to see whether this is finite or not, but yes, it can be evaluated. Okay, now let's see. Using this, what we can do is as follows. Limit x tends to infinity f of x. Now this limit can be written using the fundamental theorem of integral calculus. Imagine this was integrated from 1 to infinity, And if it was, then what would we get? We would basically get f dash x dx, and when it was 1 and this was infinity, you would get f of infinity minus f of 1, correct? But we only want f of infinity simply limit x tends to infinity fx. So what we can write is, if you take the f of a to this side and simply write this, you can write it like 1 plus 1 to infinity f dash x dx. True? Because when you evaluate this, you get limit x tends to infinity f of x minus f of 1, which is simply 1, and they will cancel up, and it would basically give you the answer. Okay. Now, this can be written as 1 plus 1 to infinity dx by x square plus fx whole square, correct? This is the integral you have. But remember that since f is an increasing function, we can always write that since x is greater than 1, we can write that fx is greater than f1, right? Which is nothing but 1. And since fx is greater than f1, this quantity here should be less than 1 to infinity, since fx is in the denominator, dx by x square plus 1, correct? And if you were to evaluate this integral, the antiderivative of this is basically tan inverse x. Tan inverse infinity minus tan inverse 1 simply would give you 1 plus pi by 2 minus pi by 4, which is nothing but 1 plus pi by 4 as desired by the question. So limit x tends to infinity does exist and is less than 1 plus pi by 4. It is bounded by that value. So this is how we can use the fundamental theorem of integral calculus and monotonic functions to find out the value. This type of questions can come as often as you want, and this can come in both forms, either in subjective form or in objective form, because for subjectives you have to show all this, and even for objectives you need to do all this to find the upper bound, which could be posed as a problem of JEEs. And it has been seen before to find out bounds of functions. You are using integral calculus and differential calculus before. Okay, so I hope the problem was clear. Let me know in the comment section if you have any suggestions, and thank you for watching. Please do subscribe to the channel.
Hello everyone, welcome to this problem. Today we are going to solve this integral, and this is a very interesting integral actually, because of the integral and then the square root, and then there is an infinite product inside as well. Okay. So as you can understand from just taking a glance at this, that what we need to basically achieve is find the value of this infinite product. So I will write it separately here. Let this be S theta. Some product of k equals to 0 to infinity cosine of theta upon 2 to the power k plus 1 by 2. So this is the infinite product that we need to find the value of. Now, so from basic trigonometry, what we can infer directly from this equation, okay, so this might be a bit hard to observe at first, but if you just ignore this theta by 2 to the power k part and consider this as an angle, so let alpha equals to theta by 2 to the power k, and only focus on the expression inside the product. So that thing basically comes out to be cos alpha plus 1 by 2, right? And if you remember correctly, this is simply nothing but cosine of alpha by 2. That is the product for the half angle formulas, right? That is the formula for that. So we will use this, and in this way, our S theta should become product of k equals to 0 to infinity cosine of, so it was alpha by 2, so it would be theta by 2 to the power k divided by 2. That 2 will get absorbed in the denominator, which would result basically in theta upon 2 to the power k plus 1. Okay, so that is an infinite product. But how does that help us? Well, what we are going to do is we are going to exploit an identity, and we're going to extend it in such a form that we get our answer. We'll start with the most basic function sine theta, and we'll apply the half angle formula for sine theta, which is, I will write it here. You know that sine 2x is simply 2 sine x cos x, right? 2 sine x cos x. Now consider x as theta by 2 here. So sine theta is basically sine of 2 times theta by 2, where this theta by 2 can act as our x, And this should simply give you 2 sine theta by 2 cos theta by 2, right? Again, do the same thing with sine theta by 2. What will you get? You will get something like this. 2 sine theta by 4, and there is a 2 square because there is another 2 getting absorbed in this one. Cosine of theta by 4 into cosine of theta by 2. Do it again with sine theta by 4, you will get 2 cube into sine of theta by 8, cosine of theta by 8, cosine of theta by 4, cosine of theta by 2. Do you see where this is heading? So when we expanded it 3 times, what we got is 2 cube multiplied by sine of theta by 2 cube, and then from cos of theta by 2 cube all the way up to cos of theta by 2. So if we were to do it n times, like we expand it n times, what we would get is something like this. 2 to the power n sine of theta by 2 to the power n, and then there would be cos of theta by 2 to the power n into cos of theta by 2 to the power decreases, right? So if it was 2 to the power n here, it should be 2 to the power n minus 1 here, and this should go up to cos of theta by 2. That is our identity, correct? So that basically means that what we can write from this equation, since we know that this is equals to sine theta, right? What we can write is this finite product here basically, which can be written in the form k equals to, let's say 0 to n minus 1 cosine of theta by 2 to the power k plus 1. Notice how the limits will manage it, because k equals to 0 will produce you a cos of theta by 2, and k equals to n minus 1 will produce you a theta upon 2 to the power n, right? So that is correct. Should basically be equal to sine theta upon 2 to the power n sine of theta by 2 to the power n. So this is what we have. If you take limits on both sides, let's say you take limit n tends to infinity, since n is just a variable here, as we have assumed, it's an positive integer. So we let n tends to infinity, right? What happens is we write this product up here. We'll evaluate it on the next step. This cosine of theta upon 2 to the power k plus 1. And what happens on the right hand side is sine theta is left out because it is not a part of the limit. But what we do evaluate is this limit. Limit n tends to infinity 2 to the power n into sine of theta by 2 to the power n. Correct? The left hand side simply becomes a required product s theta. So if you go back and see what s theta was, this was s theta. And this is what it has become, because the n basically goes to infinity. And s theta becomes sine theta upon. Now, how do we evaluate this limit? So we can transform it into one of the forms we do know. So if you let y equals to 2 to the power n here, you see that y also goes to infinity. So the limit can basically be written as limit y tends to infinity sine of theta y divided by y. Now this, y tends to 0. If you let, I meant 1 upon 2 to the power n actually. That is what we want to do, because yeah, we can do y into sine of theta by y, but then again we have to substitute for 1 by y. So we rather want y equals to 1 upon 2 to the power n, so it goes to 0 directly, and we can substitute it directly here to get this form. And why do I want to get this form? Because obviously there is a standard limit extends to 0, sine x upon x, which is equal to 1, right? And this can be proved easily either using L'Hopitas or using the Taylor expansion of sin x, which is 1 x minus x cubed by 3 factorial, then plus x cubed by x to the 5 by 5 factorial, and all the odds, right? So sin is for the units. Okay. So what this will get you is sine theta upon this thing is basically equal to theta, right? So you can adjust a theta y here and a theta here, and this whole thing will go to 1. So this answer is basically sine theta by theta. And our required integral I, which was the infinite product, now simply boils down to the integral 0 to infinity sine theta by theta d3. I'm not going to evaluate this integral because I have already shown in great detail how to do this. You can find the link to this video on the top right now. And this is basically equals to pi by 2. You can do this using Feynman's trick of integration or differentiation under the integral sign, also using counter integration or complex statistics instructor. Okay. So the final answer for the integral should be pi by 2. So that is just a representation of this integral. This integral comes in many forms. So that would be the answer. Okay. So if you really like this video, please do subscribe. Let me know in the comment section what you think about this. Thank you. Hello everyone. Welcome to NS Academy. So today we're going to look at this integral 0 to 1 ln of 1 minus x upon x dx. Now, this is in traditional sense not a very clear integral to approach to, like not any fundamental methods are going to work on this one. We can call this integral I. So that is why I'm going to show this integral and how to approach integrals of the same time. So in order to do this integral, you might think of a few tricks that you have learned while doing this kind of integrations or where logarithm is associated to it. Like let's say putting x equals to sine square theta or cos square theta and stuff like that. But in this case, what we need to do is we need to understand the expansion of log of 1 minus x around the point 0. And this turns out that this basically is minus x squared upon 2 minus x cubed upon 3 and so on it goes. In summation notation, we can write this as minus summation n equals to 1 to infinity x to the power n upon n. And this only works if x is between minus 1 to 1 strictly. So it cannot be equal at the endpoints, obviously. Otherwise, you do know that log of 0 goes up to negative infinity. So these are the limits that we need in order for the expansion to work. And it is the range in which this logarithm of 1 minus x converges. So in order to do our integration, we are going to use this expansion. So we can rather write here integral of 0 to 1. And in place of ln of 1 minus x, we can simply put in this summation expression instead of ln of 1 minus x, which is summation minus n equals to 1 to infinity x to the power n divided by n. And then there is a 1 by x there, dx. And on simplifying a bit, you get that this is simply 0 to 1 minus summation n equals to 1 to infinity x to the power n minus 1 by n dx. Now, up to this point, it should be clear. And how we arrived at this expansion is something we can talk about in other videos. This is called the Maclaurin expansion. It's called the Maclaurin's expansion. And this is a very general, specialized form of Taylor's expansion. You might have heard of Taylor's expansion if you're doing your basic calculus right now. Not basic in the sense, but the expansion which is required in most. So I can just show it here a little bit. For any function f of x that is differentiable up to some order, you can do a partial sum. And if it's differentiable continuously, you can simply write an expression like this: f of x equals to f of 0 around the point 0, of course. Then f dash 0 multiplied by x, then f double dash 0 upon 2 factorial into x square, and so on. Assuming that f is differentiable at the point 0 continuously, that is, for all derivatives are defined. So this is called the Taylor expansion. So more about that later in some other video. So what we can do here is now, in this expression, we can interchange the summation and the integral basically. And that is allowed because this whole thing, it's a completely positive quantity since x is between 0 to 1. If you ignore this negative sign outside, this just basically comes out. And also the sum converges because in the range 0 to 1, we have seen that logarithm converges, right? So using the dominated convergence theorem, or you can simply put it like this, that if you have something which converges absolutely here, you can simply put this value. So this is not an alternating sum, right? And this thing converges and all the terms are positive if you do not take care of this negative sign because it basically comes out. You can write this expression n equals to 1 to infinity 1 by n into x to the power n minus 1 dx. So x is the integration variable here. So the whole summation can just basically come out like this. N equals to 1 to infinity, 1 by n, and then you have 0 to 1, x to the power n minus 1 dx. Now this is a fairly simple integration. You know that this is equals to 1 by n, and thus the integral basically turns into negative of n equals to 1 to infinity, 1 upon n squared. And this simply is 1 by 1 square plus 1 by 2 square and all the way up to infinity. This is the particular case of the Riemann zeta function, and you can write this basically like this: zeta of 2, which is a given value of pi square upon 6. So basically, the sum of the square of the natural numbers reciprocals when added up to infinity gives you a pi square by 6, which is like very weird, but we do have lots of proofs on this one, and I also intend to show some of them, not in this video though. But the Riemann zeta function basically is defined like this: the infinite sum of from n equals to 1 to infinity, 1 upon n to the power s. And notice that the power s can also be a real complex number. It does not only need to be a real number. And this is defined, this thing converges when real part of s greater than 1. So this is how the Riemann zeta function can be defined in terms of real numbers at least. And the answer to this integral is minus of pi square upon 6. So I really hope that you like this video. But the explanations for this Taylor expansions and of course the Riemann zeta function and special values like zeta of 2, zeta of 3 is irrational, then zeta of 1 diverges, zeta of 1 is basically your harmonic series, stuff like that. I wish to put a lot of this on this channel. Thank you for watching.
Hello everyone, welcome to this video. In this video we are going to solve integral of square root tan x dx. Now whenever we have an integral where there is a square root and this is not a standard integral, first thing we would like to do is basically find some way to remove the square root. So if it was obviously integration of root x dx, that would have been a standard integral, right? But integrals like root tan x and root cot x, those cannot be packaged like that. And as you know, in integration, we do not really have much rules for indefinite integration except for the u substitution and the integration by parts, right? Okay. So first of all, the only substitution that comes to mind to remove the square root is the most basic one. Make it a t square, right? So set tan x equals to some variable squared. So I'll choose t. Then obviously we also need to take care of this dx term. So we differentiate both sides to get sec square x dx equals to 2t dt, and therefore dx should be equal to 2t dt divided by sec square x. Also, since tan x is t square, if you square both sides, you will get tan square x equals to t to the power 4. And from the trigonometric formulas, sec square x minus 1 is simply equals to tan square x. We can substitute it for that, and therefore sec square x is simply 1 plus t to the power 4. And this term here becomes 2t dt divided by 1 plus t to the power 4. Now, with this in hand, we can write our integral I as this. Integral I then becomes root over t squared, because the tan x has been substituted as t squared, multiplied by dx, which is simply this term, right? 2t divided by 1 plus t to the power 4 dt. And if we simplify it, it simply becomes 2t squared divided by 1 plus t to the power 4 dt. Okay, so this is our resulting integral. But how is it any easier than the first one? Well, it is. If you notice this 2t square, there is something we need to do with this term in order to uh, make it solvable, like we do not really have a direct substitution here, which we can do, and then magically, the derivative of that comes in the numerator just like a new substitution, and then we finally get a result. Nothing of that sort is going on here. But what we can do is this: we can write 2t square as t square plus 1 plus t square minus 1. And there is a reason we are doing that, which you will see pretty soon. So now obviously, since integration is an additive operator, we can divide it over addition. So you distribute it over addition and find this two resulting integrals, right? T squared upon 1 divided by 2 to the power 4 plus 1 dt plus integral of t square minus 1 divided by 2 to the power 4 plus 1 dt. This should also be dt. Okay. Now, here's the part. If you see an integral which is of this form, where x square plus a square divided by x to the power 4 plus a to the power 4, something like that, but of this form directly, nothing should be changed. This kind of forms are treated in a separate manner. This forms are treated by dividing up and down by t squared. So what will you get? You will get something like this: 1 plus 1 by t squared divided by t squared plus 1 upon t squared dt. And then the next term you should get 1 minus 1 by t squared divided by t squared plus 1 by t squared dt. And then we have to write, we will keep the numerator as it is, we will not touch that, but rather we will write the denominator in the formula of a minus b whole square plus 2ab, which is a square plus b square, right? So this should be t minus 1 by t whole square plus 2 dt. Again, we will keep the numerator unchanged and the denominator, but in the other way, t plus 1 by t whole square minus 2. Are you getting a sense of where this is going? Why am I doing all this stuff that might look unrelated? This is because now we are going to substitute u equals to t minus 1 by t in this first integral, and we are going to substitute v equals to t plus 1 by t in the second integral. This is because the derivative of t minus 1 by t is basically 1 plus 1 upon t squared dt. If you find it, this becomes 1 plus 1 upon t squared dt, which is simply the value in the numerator of the first integral. And similarly, dv is 1 minus 1 upon t squared dt, correct? So this gives us the following. This becomes du, the numerator, and the denominator becomes u squared plus 2. Similarly, the numerator again becomes dv, and this becomes v squared minus 2. Now, there are standard integrals to find out this, and I will jot it down right here. Many of the standard books will give you this result. The first one basically is this: dx upon x square plus a square, where a is a constant, is 1 upon a tan inverse of x upon a plus c. This is the first result. And the second one, dx upon x square minus a square, where again a is a constant. This one is rather a different one. Obviously, it has nothing to do with tan inverse this time. It's natural log of x minus a upon x plus a plus c. So these are the two results that directly compare to these two integrals right here, as you can see. So in the first integral, du upon e square plus 2, our a is basically root 2. If you can notice, 2 is root 2 whole square, right? So that one becomes 1 upon root 2 tan inverse u upon root 2, and the next one is simply 1 upon 2 root 2, again a is root 2, log of v minus root 2 divided by v plus root 2 plus c. Okay, now what was u? U was, I think, t minus 1 by t, right? U was t minus 1 by t and v is t plus 1 by t. Okay, so therefore integral of root tan x dx now becomes 1 by root 2 tan inverse of t minus 1 by t by root 2 divided plus 1 by 2 root 2 logarithm of t plus 1 by t minus root 2 divided by t plus 1 by t plus root 2 plus c. And again, t was root tan x, so we can simply write this as 1 by root 2 tan inverse of root tan x minus 1 upon root tan x divided by root 2
plus 1 by 2 root 2 logarithm of root 10x minus 1 by plus 1 by root 10x minus root 2 and divided by the same thing, root 10x plus 1 by root 10x plus root 2 and add a plus c, do not forget that. Okay, so this will complete our derivation of integral of root 10x. So this is the final answer, but obviously this might look complicated. No one is going to guess this answer, right? That yeah, here is this function, you can differentiate it and obviously would get root 10x. That's not obvious at all. But well, if you know the methods of how to approach this and problems of similar kind, so you can try root cortex yourself right after doing this to see what are the differences between them and how are they connected actually. So anyway, that would complete the video. So please like and subscribe and let me know in the comments if you have any requests for any other videos. Thank you.
Hello guys, welcome to NS Academy. So in this video, we're going to look at a problem from JEE Advanced 2024. So this was from JEE 2024, and this was I think problem 1 from paper 1, and it's a very interesting problem actually because of the simplicity it bears. So this problem is a very common pattern or common type of problem that appears in many previous versions of JEE and in other exams as well. And here you can see, let us read the problem once first. Let f of x be a continuously differentiable function. When we say continuously differentiable, it means that the function can be differentiated and all higher derivatives of this function exists. So basically, if you choose a positive integer n, then the derivative of fx done n times will also exist. That is what continuously differentiable means. And it is continuously differentiable on the interval 0 comma infinity, that is on the positive real line, such that f of 1 equals to 2, an information we would require later. And we are given that for each x greater than 0, this equation holds. So this is an equation involving limits and the function f of x and some polynomials t to the power n and x to the power n, x to the power 10, and we have to find f of x for all x greater than 0. Now, what I really wanted to show by choosing this problem is the pattern encoded in this kind of problems. So the limit we are given is simply this: limit t tends to x, t to the power 10 f of x minus x to the power 10 f of t divided by t to the power 9 minus x to the power 9 equals to 1. Correct? Now, this is very familiar to some standard limits that we already know. I will write down those two limits. So that is the first thing that should pop in your mind. That okay, so what can I relate it to? Obviously, if it's of the form 0 by 0, you can do Lapita and you can basically simplify it down. But what if you are not allowed to do that, or what if you do not know those advanced methods? Can you do it still using the methods that you have learned in class 11th and class 12 or your 11th and 12th grade? So the standard limit that basically falls in place is this: limit x tends to a, x to the power n minus a to the power n, by x minus a is basically equals to n a to the power n minus 1. This is a limit that we will require because you see, why am I writing this limit? Why did this feel important here? Because of the pattern. We have a t to the power 9 minus x to the power 9. We also have t to the power 10 into something minus x to the power 10 into something. So this x to the power n minus a to the power n, this thing basically appears in the denominator, and it appears in a disguised way in the numerator as well. Also, this fact can be used, and if we cannot use it directly, we would find a way to use it indirectly. So how do we do that? So that is what I do in most of my problems. So you see there is a t to the power 10 f of x, right? But we don't need the f of x. How do we basically vanish it? Well, one way is to force it, which is we subtract from it something which has the term f of x, so that f of x can be factored out. And what we basically want is x to the power 10. So that when you factor out f of x, you basically get t to the power 10 minus x to the power 10, and that is something of the form x to the power n minus a to the power n, and the limit also supports it since it's t tends to x, as here it was x tends to a, right? But we cannot just introduce a term, we also need to add it to make things equal, like this, and then just write down the rest of the expression.
and we should get something like t to the power 9 minus x to the power 9, and this is equals to 1. Okay, now we can use distributive law to separate these two parts of the limit because they exist independently, and we can do this and we get limit t tends to x, factor out f of x. In the numerator, write down t to the power 10 minus x to the power 10 as expected, and in the denominator, t to the power 9 minus x to the power 9. And then from this part, obviously we can take x to the power 10 common, but we would rather take minus x to the power 10 common, which also is outside the limit again, because x is not a limit variable, it's basically a constant in terms of the limit, which we can also do for f of x. In the next step, we will do that. Limit t tends to x, and we have f of t minus f of x divided by t to the power 9 minus x to the power 9 equals to 1. Okay, so we factor out f of x here, and now this part in the limit, this is reminiscent of the one we did here, the standard limit, but something is missing, right? So the x minus a factor is missing. How do we get that? Well, we can obviously divide numerator and denominator by x minus a, which in this case is basically t minus x. And remember the basic fundamental of limits, we can do that because t minus x, even though t tends to x, t minus x is not 0 because t tends to x. That means t is never equal to x. It's infinitely closer, but it's never equal. Okay, so when we divide up and down by t minus x, we can simply write this as the quotient of two different limits like this by t minus x and then minus x to the power 10. And similarly here we divide up and down by t minus x. We get f of t minus f of x divided by t minus x, and in the denominator we get limit t tends to x, f of not f of t, this was t to the power 9 minus x to the power 9 by t minus x, right? And equals to 1. Okay, so using our formula, we get this one as equals to f of x into 10x to the power 9, and this one is 9x to the power 8 minus x to the power 10 multiplied by, you can see this is basically the definition of derivatives, right? The rate of change of a function. So f of t minus f of x by t minus x as t tends to x is simply the derivative of f of x. So it's basically f dashed of x, the derivative of f at the point x. And divided by, we have the same formula applied again, 9x to the power 8. And we have equals to 1. Okay, so we can basically cut off x to the power 8 and x to the power 9 here to get x. Similarly here x to the power 8 and x to the power 10 to get x squared. And what we basically have here after all is 10x by 9 f of x minus x squared by 9 f dashed x equals to 1. Okay, now we want to make the leading term of the leading coefficient of f dash x as 1, so that we have it in a linear differential equation format, because you can see it's a linear differential equation and we would need an integrating factor to easily solve it. So we multiply both sides by minus 9 by x square, so that you know the reciprocal of this basically, so that it becomes 1. So obviously this becomes 1, that coefficient of f dash x. But what happens to this? 10x by 9, I have already introduced a minus sign because we are multiplying by minus 9 by x square, and we have 9 by x square, right? And then we have f of x, and then we have minus 9 by x square. Okay, simplify this, x and x goes off, and 9 and 9 goes off, you have an x left over. So you basically have the equation f dash x minus 10 by x f of x equals to minus 9 by x square. Okay, now it's simply left to do find the integrating factor. We know the integrating factor is simply e to the power p dx, right? Where p is the coefficient of f of x. So it's basically minus 10 by x. Now what is this? This should basically be 10 ln of x, which you can write as e to the power ln of x to the power minus 10, because the coefficient goes inside the log. And since ln also has base e, this is simply x to the power minus 10. So we multiply both sides by x to the power minus 10, and we see x to the power minus 10 into f dashed of x minus 10. This was already an x to the power minus 1, so we just multiply x to the power minus 10 to that, and we get x to the power minus 11. F of x is equals to minus 9 by x square into x to the power minus 10. Okay, you can see this is basically d dx of f of x into x to the power minus 10, correct? And this one it becomes, I think, minus 9 into x to the power minus 12. Okay, now we integrate both sides. We get f of x divided by x to the power 10, and remember that x greater than 0, so all of this makes sense, is equals to minus 9 integration of x to the power minus 12 dx. Now, okay, so according to this is one of the simplest integrations, obviously, and this would simply give you x to the power minus 11, I guess, by minus 11. Okay, and there would be a plus c. You would get f of x by x to the power 10 equals to, so the minuses will cut off. It will have 9 by 11 x to the power 11 plus c, correct? Now, we were also given the information that f of 1 equals to 2. We can put this in this equation to get 2 by 1 to the power 10 by 9 by 11 plus c, which should give us c equals to 2 minus 9 by 11, which is 22 minus 9, which is 13 by 11, right? 13 by 11. Therefore, f of x simply turns out to be x to the power 10 whole into 9 by 11 x to the power 11, and c is how much? 13 by 11, right? 13 by 11. Multiply this and you get 9 by 11x plus 13 by 11 x to the power 10, which is our answer for f of x. Now let's go back and see which one matches our answer. So 9 by 11x and 13 by 11 x to the power 10. So option B is the correct answer. So as you can see, this kind of questions, when you are doing it mentally, you are basically trying to speed run it. You are like, okay, so this is there, this is there. I can do this step. You know, this step should come immediately to your mind. So if not, you just remember this step from now on and try to apply it in situations where you see this kind of things are happening, to add and subtract something which would make the sum particularly easier. So once you arrive at this equation, this differential equation, then it's not so much hard again, because then it's basically the simple formula. So you can afford like 4 minutes, 3 to 4 minutes for a problem like this. And once you get better and better, you would require much less time. But then again, obviously, you could have done Lapita if you would have known that. And Lapita would simply give you the differentiation of top and bottom. And if you differentiate the top side, you get 10t to the power 9 f of x minus, and then f dash t x to the power 10. And denominator would have got you, I think, 9t to the power 8, right? And then you just put, because since now this would give you, one put x equals to 9, this would not give you a 0 by 0 form. You can simply put the value of x, and this would give you 10x to the power 9 f of x minus f dash x into x to the power 10, and this whole thing would be divided by 9x to the power 8, right? And then you could get the differential equation directly from there. So these are the two ways you can solve it. So Lapita is something I do not really want to cover in this video, which is why I have not stressed on this, but I wanted to show the basic way to do this. And Lapita is obviously a easier way to solve this kind of problems. But okay, then if it was a subjective problem, I think you have to basically state the Lapidus theorem, because you cannot use a theorem without stating it in any higher exam, which is subjective. Anyway, so hope you like this video. Let me know if there is something else that you would like to see. Welcome everyone. We are going to discuss a very special integral today. And if you are here from the short, you know what the integral is. It is 0 to infinity sine x upon x dx. Now, why I say this is a special integral, because this appears in many instances of physics in applied maths, and as you study higher physics, this integral keeps coming up. So this almost is taken as a standard result. And the value of this as I have already revealed in the short and I will reveal in this video as well, is pi by 2. So this basically goes to pi by 2. It is curious because the integral of 1 upon x diverges while the integral of sin x upon x does not diverge. And interestingly enough, if you also do sin x upon x whole square, that is in fact also equal to the same integral 0 to infinity sin x upon x whole square dx. That is also equal to pi by 2. Well, that is fascinating actually. But this pattern does not really continue for long. From 3 onwards, the power 3, it becomes different. And we can also generalize it for any positive integer n. But that is going to be a bit tougher. So we'll focus on the basic integral, the fundamental one here. So how do we solve it? Well, one way to solve it is using contour integration, and that is using complex residues. But we will focus on real methods here. So define a function called f of a, and let this function be equal to 0 to infinity e to the power minus ax sin x upon x. And you have to say that a is greater than 0 and a is a parameter here. Okay, a is a variable. Let's consider a as a variable. We are doing this because we can prove that this integral basically converges and it is allowed to do differentiation under integral sign in this integral. That can be proved using the Fewin's theorem. And once we have that, we can differentiate both sides to get f dash a, which is 0 to infinity e to the power minus ax, and we are differentiating with respect to a, right? So minus x should be as a coefficient multiplied by sin x upon x dx. If you cancel off the x, you basically get the following integral 0 to infinity e to the power minus ax, and there's a minus sign outside, sin x dx. Okay. Now, what is this integral and how do we solve it? First of all, remember that sin x is the imaginary part of e to the power ix. If you do not know this result, this would be covered in the complex numbers video. And this is from the famous mathematical equation e to the power ix equals to cos x plus I sin x. Continue this to get minus imaginary part of. Now, inside you can write the whole integral. So what does the integral become? It becomes e to the power minus ax into e to the power ix. If you take minus x as the coefficient, this becomes a minus I dx. Okay. So minus imaginary part of, and now what we do get is this. Since 0 to infinity e to the power minus any positive constant mx basically gives you 1 upon m, you can just do the indefinite integral and find out. This gives you 1 upon a by I. Multiply by the conjugate and stuff like that. You know how to find the real and imaginary part. So a plus I and a plus I you have to multiply on numerator and denominator. And what you would get is something like this, a plus I divided by a square plus 1. Well, the imaginary part is, of course, when you separate this and get the imaginary part is 1 by a square plus 1, right? So we get minus 1 upon a square plus 1. And that is the value of f dash a. Now, if f dash a is that, we can integrate f dash a to get f dash a dA equals to, remember that a is a parameter and that is why this is possible, dA upon a square plus 1. What does this get us? This gets us minus tan inverse a. That is the antiderivative of 1 upon a square plus 1. And on the left hand side, we get f dash a. The fundamental theorem of integral calculus tells us that obviously we can apply limits here as well. So the limits what we want to apply here is something like this. So we know that f of 0 is our required integral, right? Because f of 0 basically gives you sin x upon x. And if you do f of infinity or a tends to infinity, that basically gives you 0 because the first term here basically becomes 0. Okay, so we can do the limits like this, infinity to 0. Similarly here, infinity to 0. The fundamental theorem of integral calculus would tell us that this is equals to f0 minus 8 limit 8 tends to infinity f of a. And similarly here it would be tan in, so basically this would be not the integration. This basically would be like this because we have already performed the integration. This was just a writing mistake. Okay, like this. So minus tan inverse 0, which is 0, and then minus tan inverse of infinity, which is minus pi upon 2. because you know tan of pi by 2 goes to infinity. Also, we have discussed that this is 0. This means that f of 0 should be equals to pi upon 2, or in other words, sin x upon x, the integral of which from 0 to infinity dx should also equal pi upon 2. And that completes our integral. So, this is the result that we have been talking about, and now I also discussed about the result here about like the sin x upon x whole square and the generalizing it. So I really want you to give a try to this one first, and then you can also give a try to doing the generalized one, which is more useful of course, because you can basically put in the value of n and get any answer. But anyway, I will make a video on that as well later on. But if you like this one, if you like this explanation and the short, and you want to see more of this, please do subscribe. And if you can, please leave a like on this video and let me know in the comments. And I will reply to everyone. Thank you.
Hello everyone, welcome to this video. Today we are going to look at this integral. Now, this is a very advanced integral that I'm going to solve for the first time on this channel, and I really hope it gets as much attention as it deserves. So this is a variant of a problem that got asked in a Cambridge entrance examination, specifically of the type 1B. But what we are going to do is we are going to find a general way to ensure that we find all such values of integrals of this pattern. Okay. So there are a few things you must know in order to do this integral, because this is not going to be a basic integral, although not so much advanced. Like let's rate this integral out of 10. If I were to do that, I would do a 5 by 10 maybe, but still pretty much advanced than basic. Okay. First of all, I do not see a straightforward way basically to solve this integral directly. And people might try to do substitutions like log x and stuff like that, and I do not know that will like whether that will work or not. But my initial intentions, whenever I see a log x to the power something and then a polynomial equation in the denominator, and then you have like 0 to infinity and stuff like that, I immediately recall the identity ddx of a to the power x equals to a to the power x log base EA, of course. And this is the identity that we're going to base the whole problem of. Now let me show you how. So first define a function with respect to a parameter s as follows: 0 to infinity x to the power s divided by 1 plus x dx. Now there's a specific reason of doing so. Let's make this x square actually. There is a specific reason of doing so. First of all, you have to notice that this is a convergent function. So this function converges, but only for values where 0 less than s less than 1. And also, this function, if you were to differentiate this function like 4 times, so basically this thing would give you 0 to infinity x to the power s. And as I told you earlier, we are going to differentiate with respect to s and not x, because we cannot even differentiate with respect to x because it's a dummy variable, right? It's inside the integration. It's not really a variable. It's just acting as one. But s is a real variable here, with which respect to which the function is defined and the answer is got. So we can differentiate with respect to s. And if we were to follow this particular formula right here, what we would get is every time we differentiate x to the power s, we'll simply get x to the power s times a constant, which is a constant with respect to s, which is log x. And by doing it 4 times, we will get 4 times that constant, which is log x to the power 4 divided by 1 plus x squared dx. Make sure you do not have any doubts here. Okay. Like when you're differentiating with respect to s, you can imagine this situation where x is the variable, where s is the variable, and x here is the constant, which here in case is a. And that is why every time you get the same thing multiplied by log x. So in this case, log x. And now if you put 0 in this function, you get your desired integral, which we are trying to find out, which is log x whole to the power 4 by 1 plus x squared dx. So our goal should be to find the function f and then differentiate it 4 times and then put the value 0 and finally get the answer, correct? Okay. Now, how do we do that? Let's see. So first of all, f of s is simply 0 to infinity x to the power s divided by 1 plus x squared dx. make the substitution t is equals to x square. This would give you, I think, dx equals to dt by 2 root t, because x is root over t, and then you differentiate both sides. You get dx equals to dt into differentiation of root t with respect to t, which is 1 by 2 root t. Put this value in. The limits will remain unchanged because for value x equals to 0, t also goes to 0. For value x equals to infinity, t also goes to infinity. And x to the power s basically becomes x to the power t by 2. 1 plus this one becomes, I think, 1 plus t. By the way, okay, x to the power s actually becomes x to the power s by 2, not t by 2. Okay, so this ensures that we have dx left only, which is dt upon 2 root t. And okay, wait. You need to make this one t to the power s by 2. That's what I was confusing here. So this is t to the power s by 2. And finally, the integral basically becomes 0 to infinity. Let's put the half outside, t to the power, and this becomes 2 to the power minus half, s minus 1 by 2 divided by 1 plus t dt. And now I'm going to introduce another function, which is like a variant of the beta function. So in general, if you know the beta function, or if you don't, I can make a video on it, or there are multiple videos already available. It's like this. So the beta function in general is defined as beta of AB, where there are two parameters a and b, and the integral is 0 to 1 x to the power a minus 1 divided by 1 minus x whole to the power b minus 1 dx. And this integral simply equals gamma a into gamma b divided by gamma of a plus b, right? Where gamma a basically is the gamma function. It's also defined the gamma function here. Gamma of n is simply 0 to infinity e to the power minus x to the power n minus 1 dx. For natural numbers n, this becomes n minus 1 factorial for n belongs to natural numbers. And for other numbers, there are different values because it's simply an integral. And this is defined for obviously n greater than 0. For those values, this is defined. Okay. So anyway, what I was trying to achieve here is beta of AB also has a different form. And the different form is given by this. Beta of a comma b also has a form with 0 to infinity, which can be achieved by certain substitutions here, which is like x to the power a minus 1 divided by 1 plus x whole to the power a plus b dx. This also gives you beta of ab. Now, Euler's reflection formula is a formula which relates a certain value of beta ab to pi and sine. So, Euler's reflection formula. Now, what is this? This states that for 0 less than s less than 1, I'll just state the real version of it. 0 less than s less than 1, gamma of s into gamma of 1 minus s is simply equals to pi upon sine of pi s. That is called the Euler's reflection formula. So gamma of s into gamma of 1 minus s equals to pi upon sine of pi s. And this exact thing right here is what we are going to need, because when you see this integral right here, what we have got, okay, so let's write f of s again. F of s basically, as we have got, was half 0 to infinity. The numerator, as you remember, was t to the power s minus 1 by 2, right? We can write it as t to the power s plus 1 by 2 minus 1 divided by 1 plus t dt. Now, if I were to tell you that this is just the beta function, you might disagree, but then again, if you remember, the form with the infinity form was x to the power a minus 1. We have our a. So, of course, there should also be a here, but it's basically power 1. Yes, exactly. But then the b is basically this. This is a and this is b, and they add up to 1. That is what the power of 1 plus t is. So, basically, this is beta of s plus 1 by 2, comma, 1 minus s by 2 basically becomes, I think, 2 minus s minus 1, which is 1 minus s by, this is the beta. value of f of s. We can transform it in terms of gamma function. This becomes gamma of 1 plus s by 2, comma 1 minus s by 2. Actually, two different gamma functions divided by gamma of the sum of that, which we already know to be 1, right? And gamma of 1 for natural numbers, as you know, it is should be 0 factorial, which is 1. Okay. So the value we got is something like this, half, and then this formula, we can write this as s plus 1 by 2 into gamma of 1 minus of s plus 1 by 2. And since s is from 0 to 1, s plus 1 by 2 is also from 0 to 1, right? So we can safely say that this holds. And since this holds, Euler's reflection formula also holds. And then this value is nothing but pi by 2 cosec of pi whole into s plus 1 by 2. Okay. So that is the value of f of s. And now when you got the value of f of s in terms of a simple trigonometric function, you can easily differentiate it 4 times. I have done it already and put 0 in the value. Once you do that, the answer that you're going to get is something like this. So first of all, f4 of 0, what was our actual integral? F4 of 0 basically gives you our actual integral, right? And if you were to differentiate this function 4 times and put s equals to 0, you would basically get 5 pi to the power 5 by 32. And since this is equal to original integral, we can safely say 0 to infinity log x whole squared, so whole to the power 4, right? The whole square would be even easier. And but would be done with the same method. Even you can achieve any basically any power of log x with the same method. Plus 1 by divided by 1 plus x squared dx equals to 5 pi to the power 5 by 32. And that is the answer. So you've learned a lot of new things here, like gamma, beta, Euler's reflection formula, differentiation under the integral sign, and how to tackle this kind of integrals. But these are the things you need to know in order to solve these integrals that come at such high places, like Cambridge entrance examination or maybe Oxford math examination. And as you go up the ladder in physics and stuff, the integrals and the difficulties keep on increasing. And obviously, infinite sums are also reduced, which are solved using integrals. Okay, so if you do like this video, please like and subscribe. And also let me know in the comment section how you like this video. Thank you.
Welcome everyone to this video. Today we are going to discuss this problem from ISI 2024 entrance exam, which was conducted on May 12th. And this was the first problem of UGB. And it was given this limit, and it was also given that c is greater than 0. And we have to find all such values of t for which there is a finite real number c, and this equation holds. And we also have to find the corresponding values of c. So this was the first question of ISI 2024 B.Stat UGB examination. We are going to see how to work out with this problem and what to do if you are given this kind of problem. So those of you who are preparing for JEE and JEE Main and JEE Advanced and examinations similar to that, you might already be sensing a pattern here. Like, okay, so the numerator here, the numerator is simply 1 to the power 1 by 3 plus 2 to the power 1 by 3 and all the way up to n to the power 1 by 3. So this is the numerator. And it's inside obviously limit n tends to infinity. But this gives us a sense that we have known Riemann sums, right? So we know that if we are given something like this, limit n tends to infinity, 1 upon n, summation I is equals to, let's say, 1 to n, and there is a function inside which is integrable, and we have the argument f of I by n. Then this limit is exactly equal to the Riemann sum 0 to 1 f of x dx. This is equal to the integral, right? This Riemann sum here is equal to the integral. So that's how the transformation works. Now, in order for this to work, we will first try to do some adjustments, so that we can convert it into that form. So your first instinct should be to write it in the summation form and see what it basically is. So we can write it like this: I equals to 1 to n, I to the power 1 by 3 divided by n to the power t. So let's just work with the limit, and we do not really want to indulge with c right now. So whatever the value will come, we will obviously consider that as c. So the value of the whole limit is c, right? So this would mean that we need n to the power 1 by 3 in the denominator, right? In order to make it a function looking like this one. So let's do that. Limit n tends to infinity. So let's take a n to the power 1 by 3 in the numerator. I also put the n to the power t here. And let's also put a n to the power 1 by 3 in the denominator. I equals to 1 to n. And this would give us I by n whole to the power 1 by 3, correct? Now, this thing, we also need a 1 by n. So let's just do it as well. We have 1 by n summation I equals to 1 to n I by n to the power 1 by 3 multiplied by, and you multiply everything together. So you multiply an n, you multiply n to the power 1 by 3, and you divide by n to the power t. So this is our limit right now. So to simplify it further, this simply becomes limit n tends to infinity 1 upon n summation I equals to 1 to n I by n whole to the power 1 by 3, and you multiply it with n to the power 4 upon 3 my t minus t. Okay. So this is our limit. So what we do know is that the separate limit n tends to infinity 1 upon n I equals to 1 to n I by n whole to the power 1 by 3. This limit is finite because this is simply then equal to 0 to 1. The function, as you can see here, corresponding function would be fx equals to x to the power 1 by 3, right? So this should be like this because you substitute I by n for x. And the value of this is 1 by 1 plus 1 by 3, right? So this is basically 1 plus 1 upon 3, which if you do, you will get 3 upon 4. That should be the value. Now we want to investigate about this part, like what would happen for different values of t. So let's take some cases. Case 1. So case 1, let this be t is less than 4 by 3. When this happens, if t is less than 4 by 3, then you can see that 4 by 3 minus t is greater than 0. That means n to the power 4 by 3 minus t, this term basically has a positive power upon n, and if you take the limit of this term, it only ever grows. It never basically decreases, right? And we do know that the limit with it basically is a finite number, that is 3 by 4, right? So whenever you can show by bounding, since this is a finite number, you can show that this limit should be basically greater than this limit. And if this limit here, the n to the power 4 by 3 minus t term, which basically bounds the entire sum, if this goes to infinity, the whole thing goes to infinity. So if t is less than 4 by 3, then our L basically goes to infinity, which is not what we want, right? So t less than 4 by 3 won't work. So let's take case 2. Case 2 should be t is equal to 4 by 3. Now, if t is equal to 4 by 3, then L should be equals to limit n tends to infinity 1 upon n summation I equals to 1 to n I by n whole to the power 1 by 3, and the term n to the power 4 by 3 minus t goes to 0, n to the power 0, which is 1, right? This, as we know, is 0 to 1, x to the power 1 by 3 dx, and you get the answer 3 upon 4. And for the cases where we have case 3, that t is, I think, greater, right? Yeah, t is greater than 4 by 3. In this cases, you get the same result. So let's say you have this whole thing here. So you have this whole thing here multiplied by n to the power 4 by 3 minus t, right? But now this term basically diverges because converges, because you see, like 4 by 3 minus t is the negative, and this means that this term is basically 1 by n to the power alpha for some alpha greater than 0, and this term will always go to 0. So in that case, what happens is L becomes 0, since limit n tends to infinity 1 upon n to the power, and if you write this like this, t minus 4 by 3 is 0 because t is greater than 4 by 3, right? So 1 upon n to the power something positive, this will go to 0, and this is what is going to dominate the other limit here, which is basically a finite number as n goes larger, right? It just goes to 3 by 4, but this one goes towards 0. So that would basically give you all the possible values here. So t is equal to 4 by 3 corresponds to c equals to 3 by 4, and also t greater than 4 by 3 corresponds to c equals to 0. That is the investigation that they have asked us to do about t and c, and this is the answer. Okay, so that completes the video. Please do subscribe the channel if you want to see more of this content and also want to prepare for the upcoming ISI and CMI examinations or JEE Mains and JEE Advanced. So thank you again. Let me know if you have any other doubts in the comment section.
Hello everyone. In this video, we are going to solve the problem from the Harvard University -5 whole to the power x equals to 5. And we are to solve for the real numbers x, which satisfies this equation. Now, at first glance, this really looks very difficult because, as you can understand, -5 to the power something, that would either produce a positive quantity or a negative quantity, depending on the exponent, if you are talking about integers. Well, so like let's take a few examples. -5 to the power 1 should be 5, and if you do an even number, it should give you a positive number. But -5 to the power something, which should produce a positive number, which is 5 itself. That is something which we haven't have an idea of directly, like you cannot guess the value of x directly from here, but we will follow standard mathematical procedures here. So -5 to the power x equals to 5. If we take logarithm on both sides, it looks something like this. So when I say logarithm, I mean natural logarithm. So I will not write base e here, but from now on, we can assume that it is always in base e. Okay. So this is log of -5 whole to the power x, and this is log of 5. Okay. So due to the properties of log, obviously we have x into log of -5 equals to log of 5. So the whole problem basically revolves around finding this part. Now, as you all know, log is not defined for numbers which are negative. So you might have seen before in your calculus 1 courses or in your basic algebra courses that log x is defined when x is greater than 0. Yes, that is true, but that is only for real numbers. Log is also defined for complex numbers, and then the input can be basically anything. We do not really care. So -5, there is some complex number, and to be fair, a set of infinitely many complex numbers, the logarithm of whose basically gives you -5. So first of all, we will write -5 as 5 times -1. And then, if you remember the most important equation in mathematics, or rather the most beautiful equation in mathematics, it was e to the power I pi equals to -1, right? It really connects all four important constants together. This is also true for any. So let's first understand how this comes into being. So like e to the power I pi, right? This is, according to Euler's formula, this is cos pi plus I into sine pi. And that is what basically brings about the -1, because cos pi is -1 and sine pi is 0. Now, what happens if you, like, let's say, replace it with other variables, right? So let's say if we were to do something like this, cos of 2n plus 1 pi, we are ensuring that 2n plus 1 is always odd. That means cos of 2n plus 1 pi will always be -1 plus I into sine of 2n plus 1 pi. And any integral multiple of pi with sine always gives you 0. So even this equals -1, right? So that is why what we can do is we want to generalize it for n, because that is important in a logarithm with a negative number inside it, because we can do the principal branch, but then also we can make several other values which will also correspond to log of -5. So there is not a single value which corresponds to log of -5 in complex numbers. Okay. So -5 is 5 into -1, and -1, as we have just seen, is e to the power 2n plus 1 whole into pi into I multiplied by 5. So that should be, because this term, according to Euler's formula, transforms back to this term, right? Okay. Now, log of -5 then should be equal to log of the right hand side. So using formula of logarithm, we can divide this we can separate this multiplication task into two different terms, which are basically added. So log 5 plus log of e to the power 2n plus 1 whole into pi into I. And this gives you log 5 plus, since the base is e, this thing comes out 2n plus 1 pi I. And now if you go back to our problem, it was x into log of minus 5 equals to log of 5. Correct? So this gives us the value x is equal to, also we will make some changes right now after we write this expression, log 5 divided by, so log of minus 5 as we know is now log 5 plus this. So we can do log 5 plus I pi 2n plus 1 for all n belongs to integers. This will work. And you can explain it further by using the fact that 5 is basically equal to 5 into e to the power 2mi pi for any integer m. So you can also write the same thing, and the numerator becomes log 5 plus 2mi pi, and then the denominator becomes log 5 plus I pi 2n plus 1 for all n belongs to integers. And this is the solution to the equation. So if you like this video, please subscribe the channel and like this video, and let me know in the comment section if you want further stuff like this. Thank you.
Hello everyone, welcome to INS Academy. Today we are going to solve this integral. So this is a fractional part integral, and I chose this integral because I wanted to explain the properties of fractional parts, and I also wanted to explain some properties of definite integration. So by the end of this video, we will be feeling comfortable in both fractional parts and definite integration, because we are going to use a lot of properties here. So look at this integral carefully first. 0 to 1 fractional part of 1 upon kth root of x. So the whole thing is inside the fractional parts, and we have k greater than or equal to 2. Now, it might seem impossible for you to even start this problem if you are not aware of the fractional parts. So I will say that fractional part of x simply means it's a number between 0 to 1 where it cannot be 1. And some examples would be 0.2, the fractional part of this is 0.2 itself. 1.5, the fractional part is 0.5, like that. So it basically gives you the fractional part, not the integer part. Okay. Now, how do we do this? So we will begin with the obvious substitution, x equals to t to the power k. So x equals to t to the power k. With this substitution in hand, we can write dx equals to k into t to the power k minus 1 dt. Notice that the limits remain 0 to 1. So our integral basically becomes 0 to 1. Fractional part of 1 upon, now since kth root of x is then t, this simply becomes 1 by t, and dx as here becomes k into t to the power k minus 1 into dt. This much is done, right? Now we make a substitution, u equals to 1 by t. So this would mean that t is equals to 1 by u, and then if you differentiate both sides, it will give you dt equals to minus du by u square. Notice the limits. For t equals to 0, u is infinity, and for t equals to 1, u is 1. Inside we have fractional part of u, k is as it is, let's put it outside, and then t to the power k minus 1 becomes 1 by u to the power k minus 1, and dt becomes minus du by u square. We can simplify this and write this as k 1 to infinity, since the minus sign basically reverses the order of integration here. Fractional part of u divided by u to the power k plus 1 du, and we reach this point, and that is the goal in every fractional part integral of this type. We have to reach something where we have the fractional part in the numerator or the denominator simply as u. Now let's do it from here. So we have this integral now. Now in this integral, notice that fractional part of u, the important property to notice is fractional part of u can be written as u minus the integral part of u.